A microscopic fracture in a suspension bridge does not spell impending catastrophe, but instead triggers an automatic, silent repair. A spiderweb of hairline cracks in a skyscraper's foundation seals itself overnight, and the shattered screen of a smartphone knits back together like living tissue. This is not science fiction, but the very real scientific promise of self-healing materials. Inspired by the biological world, these innovations aim to eradicate the concept of mechanical failure, transforming our built environment from static structures into dynamic, regenerative systems. Exploring this frontier reveals a future where the objects around us actively fight against their own demise. The foundation of this field rests on biomimicry, the practice of learning from and mimicking the strategies found in nature to solve complex human design challenges. For billions of years, living organisms have possessed the innate ability to detect damage and initiate a localized healing response. Blood clots to seal a wound, and bone fractures calcify to restore structural integrity. Material scientists are now translating these biological blueprints into synthetic forms, engineering inanimate substances that can sense a rupture and deploy chemical agents to bridge the gap before a catastrophic break can occur. At the forefront of this regenerative revolution are polymers, large molecules composed of many repeated subunits, which form the basis of plastics, resins, and countless industrial components. Researchers have successfully embedded these polymers with microscopic fluid-filled spheres known as microcapsules. When a crack propagates through the material, it ruptures these embedded capsules, releasing a liquid healing agent into the microscopic void. A secondary catalyst, already dispersed within the polymer matrix, reacts with this liquid, causing it to harden instantly and glue the fractured edges back together. In controlled laboratory environments, this microcapsule approach borders on the miraculous. Structural integrity is routinely restored to nearly 100% of its original strength within hours, with no human intervention required. The initial breakthrough echoed through the materials science community, reshaping our understanding of product lifespans and structural resilience. The quiet lab work fueled a new era of innovation, suggesting an imminent end to the cycle of manufacturing, degradation, and disposal that defines modern consumption. Yet, stepping outside the pristine conditions of the laboratory reveals a starkly different reality. If the fundamental chemistry is sound, a critical question remains regarding the challenges preventing widespread use. The chasm between a successful proof of concept and a ubiquitous industrial application is vast, fraught with engineering hurdles that expose the severe limitations of mimicking billions of years of biological evolution in a matter of decades. The most glaring limitation of the microcapsule method is its finite nature. Once a capsule ruptures and expends its healing agent, that specific localized area loses its regenerative capacity forever. If a subsequent stress fracture occurs in the exact same location, the material remains defenseless. Unlike a living vascular system that continuously pumps nutrients and repair cells to a wound site, synthetic polymers lack a circulatory network. Creating a true artificial vascular system capable of delivering continuous healing agents throughout a solid material introduces a level of manufacturing complexity that current industrial infrastructure simply cannot support. To bypass the one-time use limitation, engineers are exploring intrinsic self-healing materials. Instead of relying on embedded capsules, these substances are designed with dynamic chemical bonds that can break and reform repeatedly. Imagine a network of magnetic connections. When pulled apart, they inherently seek to snap back together. Under the right conditions, such as the application of heat or ultraviolet light, the molecular structure of these intrinsic materials becomes mobile, allowing the fractured polymer chains to intertangle and rebond, effectively erasing the damage. However, this intrinsic approach introduces a precarious trade-off that directly impacts infrastructure repair and public safety. For a material's molecules to be mobile enough to heal, the material itself must often be relatively soft or flexible. If scientists engineer a bridge support column to be dynamic enough to heal its own fissures, they risk compromising the rigid structural integrity required to hold thousands of tons of concrete and steel. The very rigidity that makes high-performance materials useful is exactly what makes it hard for their molecules to flow across a fracture to initiate repair. Furthermore, the real world rarely provides the optimal conditions required for intrinsic healing to occur spontaneously. A cracked airplane fuselage cruising at 30,000 feet is subjected to freezing temperatures and immense pressure, not the gentle application of targeted heat or ultraviolet light required by laboratory prototypes. Relying on external triggers means the technology is not truly autonomous. If a human operator must identify the microscopic crack and apply a heat gun to initiate the repair, the primary advantage of a self-sustaining, self-monitoring system is entirely lost. According to leading materials scientists and supply chain analysts, the most insurmountable barrier preventing widespread use is the hard arithmetic of industrial economics. Traditional manufacturing processes have been optimized over a century to produce steel, concrete, and standard plastics at incredibly low costs. Integrating complex self-healing agents, synthesizing specialized dynamic polymers, or weaving microscopic vascular networks into a product dramatically inflates the cost of production. For a technology to achieve global ubiquity, it must not only be technically superior, but economically viable. This economic reality creates a profound dilemma for manufacturers of everyday consumer products. If a self-healing smartphone screen costs 5 times as much as a standard glass display, the consumer market will largely reject it, regardless of its technological brilliance. Companies operate on the principle of planned obsolescence, a business model that relies on products breaking down and needing replacement. Introducing a material that actively resists degradation threatens the fundamental revenue streams of global manufacturing, sparking a quiet resistance against the integration of materials that never fail. Despite these economic headwinds, some sectors are pushing forward out of sheer necessity, most notably in the realm of concrete. Concrete is the most widely consumed substance on Earth after water, and its propensity to crack under tension is a global infrastructure crisis. Researchers have developed bioconcrete embedding dormant bacterial spores and calcium lactate directly into the mix. When a crack forms and water seeps in, the water awakens the bacteria, which then consume the calcium lactate and excrete limestone, naturally sealing the fissure from the inside out. The bacterial concrete breakthrough echoed with promise, offering a glimpse into living cities that maintain themselves. Yet the ghost of those initial engineering hurdles lingered. The harsh, highly alkaline environment of wet concrete is incredibly hostile to living organisms, requiring the bacteria to be encased in protective clay pellets before mixing. This added step complicates the pouring process, alters the structural weight, and significantly drives up the cost of a material whose primary virtue is its dirt-cheap availability. Furthermore, the long-term survival rate of these dormant bacteria over decades of freezing and thawing remains an unproven variable. The slow integration of these regenerative systems forces us to reevaluate humanity's fundamental relationship with the physical world. For millennia, we have viewed materials as subservient, static entities meant to be extracted, utilized, and ultimately discarded. The advent of autonomous, self-repairing matter challenges this deeply ingrained perspective. We are standing on the precipice of an era where the objects we create possess a rudimentary form of agency, capable of self-preservation and adaptation without our constant oversight. This newfound material agency introduces unexpected environmental and ethical dilemmas. If we successfully engineer polymers that flawlessly heal themselves and resist all forms of natural degradation, we risk creating the ultimate ecological nightmare in the form of indestructible pollutants. A plastic bottle that can infinitely repair its own chemical bonds is a product that will never break down in a landfill or an ocean. The pursuit of ultimate durability must be perfectly balanced with the necessity of end-of-life biodegradability, a chemical paradox that continues to baffle the brightest minds in synthetic biology. Consequently, the first true widespread applications of self-healing technology will not be found in our homes or our highways, but in environments where human repair is physically impossible and cost is irrelevant. In the vacuum of deep space, a micrometeorite puncture in a space station habitat or a satellite solar array is a fatal event. Aerospace agencies are actively testing advanced autonomous polymers that can instantly seal a pressurized hull breach. In the unforgiving expanse of the cosmos, the ability of a material to knit itself back together is not an economic luxury. It is the absolute prerequisite for human survival. As leading futurists and material scientists project the next 2 decades of innovation, the consensus is that the transition will be evolutionary, not revolutionary. We will not wake up tomorrow to a world of immortal infrastructure. Instead, self-healing properties will slowly infiltrate high-stakes niche applications first. We will see them in the composite wings of commercial aircraft, the battery casings of electric vehicles, and the internal components of deep-sea data cables long before they reach the consumer market. The technology will mature in the shadows, quietly extending the lifespans of critical systems. The challenges preventing the immediate ubiquity of self-healing materials are formidable, rooted in the uncompromising laws of thermodynamics, the rigid realities of global economics, and the sheer complexity of mimicking biological life. Yet, the trajectory is undeniable. We are steadily moving away from an age of static, disposable engineering toward a paradigm of dynamic, regenerative design. The quest to build a world that heals itself is not merely a scientific endeavor. It is the ultimate expression of our desire to create a lasting, sustainable legacy in a universe defined by entropy.